Why does carbon form exactly 4 bonds? Why not 2, 3, or 5? And if carbon can form 4 bonds, then here's an even stranger question. Why doesn't one carbon atom simply bond with 4 other carbon atoms? It sounds perfectly reasonable and efficient, but that's not what we usually see. Instead, carbon forms bonds with hydrogen, oxygen, nitrogen, sulfur, and many other elements, while also bonding with other carbon atoms in incredibly complex ways. So what controls this behavior? Is it simply the number of electrons, the shape of the atom, or is something deeper happening inside carbon? Today, we're going inside the carbon atom to uncover both mysteries. Welcome back to Decoding Education. If you caught episode 1, you already know why carbon sits at the heart of organic chemistry. It can form an astonishing variety of compounds, more than any other element. But that raises a deeper question. What makes carbon capable of doing all this? By the end of this episode, you'll have clear answers to all of these questions. So, let's go one level deeper, inside the atom. Take a single carbon atom. Carbon has atomic number 6, so a neutral carbon atom has 6 electrons. Its electronic configuration is 1s2, 2s2, 2p2. The first shell contains 2 electrons, and the second shell, the valence shell, contains 4 electrons. These 4 outer electrons are called valence electrons, and these are the electrons that are primarily involved in chemical bonding. Now here's where things become interesting. Atoms tend to achieve more stable electron arrangements. For carbon, that means getting access to a total of 8 electrons in its valence shell. Carbon already has 4, so it needs access to 4 more. One way to achieve this is by sharing electrons with other atoms, and every shared pair of electrons can form a covalent bond. So carbon has the potential to form 4 covalent bonds. This is why carbon is described as tetravalent, but there's a problem. If we look at carbon's electron configuration more carefully, it doesn't immediately appear capable of making 4 bonds. And this is where the real story begins. In carbon's resting, ground state, look at carbon's valence orbitals in ground state. The 2s orbital contains 2 electrons, and the 3 2p orbitals contain 2 electrons distributed among them. That gives us only 2 unpaired electrons. And unpaired electrons are what's needed to form bonds. If we followed this picture literally, carbon should only be able to form 2 bonds, not 4. But take methane, CH4. Carbon forms 4 bonds with hydrogen, and all 4 are completely identical. So how can carbon produce 4 bonds when its ground state arrangement seems to provide only 2 unpaired electrons? The answer involves electron promotion. Suppose carbon absorbs a small amount of energy and 1 electron from the 2s orbital can be promoted into the empty 2p orbital. Before promotion, it has 2 paired electrons in 2s, 2 unpaired in 2p. But after promotion, there is 1 electron in 2s and 3 unpaired electrons spread across all 3 2p orbitals. Now, carbon has 4 unpaired electrons total, and every single one of them can form a bond. That solves half the mystery. Carbon forms 4 bonds because a small energy input frees up 4 electrons to bond with, but there's still a wrinkle. The 2s orbital and the 2p orbitals aren't identical in shape or energy. So why are all 4 bonds in methane exactly the same? To understand that, we need one more idea. Hybridization. Carbon takes 1 2s orbital and its 3 2p orbitals and blends them together. They mix into 4 brand new, completely identical orbitals, called sp3 hybrid orbitals. These 4 orbitals point in 4 different directions in 3-dimensional space, and the angle between them is approximately 109.5 degrees. This produces a tetrahedral arrangement. Now imagine a carbon atom at the center, with 4 sp3 hybrid orbitals extending outward. Each orbital contains 1 electron. Each can overlap with an orbital from another atom, and each overlap creates a covalent bond. This is why methane has 4 equivalent CH bonds. So we've solved the first mystery. Why does carbon form 4 bonds? Because its valence electrons and orbitals can be arranged into 4 bonding orbitals, allowing carbon to form 4 stable covalent bonds. But now, the second mystery becomes even more interesting. If carbon has 4 bonding orbitals, why can't all 4 bond with carbon? Here's the important correction. Carbon actually can bond with other carbon atoms. In fact, it does so constantly. Consider ethane. The 2 carbon atoms are connected by a carbon-carbon bond. Each carbon then forms 3 additional bonds with hydrogen. So carbon certainly can bond with carbon. But what about our original idea? 1 carbon atom in the center, bonded to 4 carbon atoms with no hydrogen or other elements involved. Is that impossible? Not necessarily. Carbon can form carbon-only structures. For example, carbon can exist in giant networks such as diamond, where each carbon atom is bonded to 4 other carbon atoms. So the statement, carbon cannot form 4 bonds with carbon atoms, would be incorrect. It absolutely can. Then what makes organic chemistry so diverse? The answer is carbon's extraordinary ability to combine with itself and with other elements. And this property of carbon bonding with itself has a special name, catenation. Carbon's true advantage isn't that it only bonds with carbon. It's that it can bond strongly with itself, again and again, almost without limit. Chemists call this catenation. Chains, branches, rings, double bonds, triple bonds. And once you start adding hydrogen, oxygen, nitrogen, and sulfur into the mix, the number of possible structures becomes almost limitless. This is the real reason carbon sits at the center of organic chemistry. Not because it prefers carbon over everything else, but because it can build stable, strong bonds with itself and with a huge range of other elements in an enormous variety of arrangements. We've now answered 2 major questions. Why does carbon form 4 bonds? Because carbon has 4 valence electrons, and its orbitals can reorganize to create 4 bonding directions. And why doesn't carbon always bond with 4 carbon atoms? Because carbon isn't restricted to bonding with carbon. It can bond with many different elements. And its exclusive property of bonding, called catenation, allows it to build chains, branches, rings, and enormous molecular structures. So, carbon's ability to form 4 bonds can be seen as one of the fundamental building blocks of organic chemistry. But understanding why those bonds form requires us to look at the behavior of atomic orbitals. How do orbitals overlap? Why do some overlaps produce sigma bonds? Why can other overlaps produce pi bonds? And how does the shape of an orbital determine the shape of an entire molecule? That's where our next topic begins. Valence bond theory. So if you want to build organic chemistry from the ground up, one concept at a time, hit the like and subscribe to Decoding Education.